So if I see the documentation, okay, for the random, so this is kind of an interesting library. You can actually generate random numbers. Okay, so there are like lots of functions, lots of methods you can say, like randrange, randint. So if you want to generate random integer from between A and B, then this is what you can use. There is a random.choice, so you can actually put some uh, basically a list inside, and it's just going to generate uh, some random choice from that particular list. Okay, you can also generate a larger sample size, by using random.choices. Okay, so you just have to supply basically how many uh, samples you want to draw, and that's what will give you you know if you use random.choices. Similarly, you have random.shuffle, random.sample. So there are a lot of random. It's just going to generate a number between 0 and 1. Okay, random.uniform. So there are a lot of them. This is generating a random number from a triangular distribution. Okay, this is from a gamma distribution. Okay, again, this is from uh, exponential distribution. This is from normal distribution. So there are actually a lot of interesting functions and uh, methods inside. Okay, so let's just try some of them. Okay, import random. Okay, so let's say you want to let's just try random.randrange. Okay, okay, so let's say 0 to 3. Okay, and let's print x. Let's see what are we going to get. Okay. So in this case we are getting 0. Okay, let's run this again and check that you'll get a different result. Okay, possibly different result. Run this again, you're getting a different result. Run this again you're getting a different result. So you can see that it's a way to generate a random number. Okay, from 0 to 3. So if you check the documentation, and just take this out. Okay, so if you check the documentation, random.randrange is basically just have to supply start and the stop and also the step. Okay, so by default the step is 1. Okay, so it's just going to generate a random number from the range that you have supplied. Okay, is that fine? Okay. So if you want to, let's say, if you want to generate 20 numbers, you can write a loop. Again, you can actually create a list. You can write a loop. So Okay, this will generate 20 random numbers from 0 to 3. So in this case, it's basically 0 will be included and 3 will not be included. So if you are generating random numbers from 0 to 3, then 0 will be included, 3 will not be included. So I think if you just change the step size, let's just try and change the step size to 0.2. I think this should work. Let's see. There's some error. Okay, so it cannot take non-integer step. Okay, let's take an integer step. I think 0 to 8. Let's take an integer step of 2. Okay, let's run this. Okay, fine. So it can only take an integer step. So now in this case, you can see that it's going to be from 0 to 8. 0 included, 8 not included. Okay, and the step size will be 2. So basically it's basically picking random number from 0, 2, 4 and 6. Okay, and this is how it's going to look. Is that fine? Okay, you can also use plot function to figure out the frequencies. Okay, so it's a histogram plot. So you can actually plot the histogram to figure out how many times 6 is appearing in the list, how many times 4 is appearing in the list, and how many times 0 is appearing in the list. Okay, so let's actually do that. Okay, so maybe let's generate 200 values. Okay, or maybe 300 values. Okay, let's generate 300 values and let's plot a histogram. Okay, show plt dot. Okay, so you can actually use hist. Okay, plt dot hist. Okay, and just put x here. Okay, and then do plt dot show. Okay, so let's run this. Okay, let me just remove this. Okay, I don't want to print out the entire thing. Okay, let me just run this. Okay, so you can see that kind of it's kind of even. Okay, so it's for 0 it is roughly 70. For 20 it is again around 70. So it's like I mean kind of uniform, right? I mean because you are generating these random numbers from 0 to 4 6, so 4 possibilities. Okay, and you're drawing 300 observations, so you can expect around 75 of them to be 0, roughly around 75 to be 2, roughly around 75 to be 4, and roughly around 75 to be 6. Which is also clearly observable over here. That it is more or less uniform. Okay, so of course if you do this exercise again, you'll get a different result. Okay, but again it will be close to 75 for each of them. Okay, and this is actually because of law of large numbers. Okay, so no matter how many times you run it, they'll be kind of approximately, all of them will be approximately 75, if not exactly 75. Is that fine?
Yes, Professor.
Okay, yeah, okay. Okay, so you can also use some other function. Let's say random.choice. Suppose you want to toss a coin. Okay, so how will you toss a coin? Well, you can actually say coin is, so you can define coin. Okay, so coin is it has basically heads. Okay, and it has tails. And then just use random.choice. Okay, and just print it. Okay, okay, let's run this. Okay, so of course I mean You tossed a coin, you got a tails. If you toss it again, of course, uh, you'll get basically different outcomes. Sometimes heads, sometimes tails. Can you see this? Every time you run. So this is how you can toss a coin in Python. Okay, and again, if you want to plot, histogram, you can do the same thing. You can basically generate a list of choices, okay, and write a loop, okay. So n is, let's say, 100. Suppose I want to toss a coin 100 times. So for by the way, here I'm writing I, but I is not really playing any role over here, no index at all. So there is another way to do it. You can just put underscore, okay. Um, that's another way in which you can do it, okay. So because it's not really playing any role, okay, uh, in the inside the loop, okay. Okay. So again, if you toss a coin 100 times, you can expect to be, roughly around 50 heads and 50 tails, because it's a fair coin. Okay. So of course, it may not be exactly 50 because it's a random sample. So anything can happen. But it's going to be, like close to 50 for heads and tails. Okay. So in this case, it turned out it's 40/60. Okay, so if you run this again, you'll get a different outcome. So in this case, you can see that there were around 46, 47 heads and around 52, 53 tails. Okay, of course, if you run this again, you'll get a different uh, outcome. So if you do this a large number of times, let's say 10 to the power 5, so basically 1 lakh tosses. Okay, so then if you just run this, you will see that they are now kind of approximately at the same level. Again, this is because of law of large numbers. If you're tossing a fair coin, then if you toss it large number of times, it is uh, they'll not be like the proportion of heads that you obtain, in 10 to the power 5 tosses, will be very close to half. It's just going to be so close to half that it will be difficult to tell the difference. So basically, this is again because of law of large numbers. Is that okay? Clear to everyone? Okay, so roughly, 50% will be approximately heads and 50% will be tails. If you just choose a large enough sample size. Okay, you can also actually have weights on heads and tails, so you can actually toss a coin, with different weights. It's kind of a weighted coin. You can also do that. Okay, so if you check the documentation, so there is a way to provide weights. Okay, so in the random.choices method. Okay, in fact, in the random.choices method, you can also directly, instead of writing a loop, you can actually directly uh, you know uh, toss a coin, just by providing this k inside it. Okay, the value of k, just feeding the value of k to it. Okay, so let's try random.choices. Okay, and let's put some weights also. Okay, okay, let's try this. You can always also do a Google search. Let's say if something is not clear from the documentation, you can actually do a Google search. Okay, random.choices Python, how to use it, something like that. I mean, you'll get lots of examples which will make it more clear, because sometimes in documentation, uh, like, examples are not given. Okay, so you want to see how you have used it, how to actually implement it. So you can actually do a Google search and find out. Okay. Okay, so random.choices coin, uh you know let's see, population weights. You can specify the weights. Okay, so let's specify weights equal to, well, maybe point 0.2 to heads and 0.8 to tails. Okay, what else? I think, okay, k, we can specify how many times we want to toss. Okay, so k is, let's say, n, 1 lakh times. Okay, and now we can just overwrite x. Okay, and let's see, let's plot the histogram for this one. Okay, so can you see that, because it's a weighted coin, so out of 10 to the power 5 tosses, roughly, 20,000 of them were heads, and approximately 80,000 of them were tails. And because it was a sample that I've chosen from a coin which was weighted. Is that clear to everyone?
Yes, Professor.
Okay. Okay, so let's continue. Okay, so you can also shuffle if you wish. You can draw without replacement if you wish. I mean, there are many functions here, that you can actually exploit for drawing samples. Okay, this random sampling is very important. Okay, I mean, extremely important. Okay, so we can also use random.sample method. So let me talk about that also. Okay, so suppose now I want to, okay, let's draw 5 cards from the well shuffled deck of 52 cards. Okay, let's do that. Okay, fine. So of course, one way to do that is basically, create, create first, the deck. Okay, so how can we create a deck? You can, so basically there are 4 suits, right? Okay, so you can create suits, maybe, so spade, then clubs, and then you have, what else? Spade, clubs, diamond, and hearts. Okay, so these are the 4 suits, and you know there are 13 ranks, right? Okay, so you can actually, let's first print out these ranks, just to see, that we have exactly 13 of them. Okay, so that's right. Okay, fine. So here, 1 denotes the ace. Okay, I mean, is that okay? Okay, so one denotes the ace, and rest of the cards are exactly the way they are: 2, 3, 4, 5, 6, 7, 8, 9, 10. This 11 is jack, 12 is queen, and 13 is king. If you don't want it, you can also create a list. Otherwise, I mean, if you want to be ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. Okay. So we can actually write a loop, to create a deck. Okay. So deck, let's say it's an empty list right now. Okay. Uh, and then all that you have to do is just write a loop. Okay. So okay, and then just keep appending the deck. Okay, deck dot append. With so basically one suit and uh, one rank. So what you can do is okay. Okay, so what I'm going to do is I'll write it in this format. Okay, so if it's an ace of spade, it will be like this: ace, spade. Okay, so I want to write something like this. So how would you do it? Well, you know, how will you do it? Well, you can actually take the rank first. Okay, so ranks j. Okay, now it's a string, right? So ranks j is a string. Okay, and then plus. Okay, like this, hyphen like this. Okay, and then plus, and then take the suit. Okay, suits I. Okay, and once I'm going to do it, I'll basically get what I want. Okay, so let's just print the deck. Okay, basically this is the full deck. Is that okay?
Yes, Professor.
Okay, and now you can actually draw something from the deck. If you want to draw 5 cards, you can draw 5 cards. If you want to draw 2 cards, you can draw 2 cards, whatever you wish. Okay, so random dot sample. Okay. So let's just quickly look at the documentation. Okay. So random.sample, you have to supply the population. Okay, and you have to supply how many cards you want to pick from the population. So population here is a deck of 52 cards, and this is basically the sample size. Okay, and you can see that it's random sampling without replacement. Basically, that's how you do provide 5 card hand in a poker, right? So random dot sample deck okay, and I want to serve a 5 card hand, okay. So let's print out the hand, okay. Let me remove this. Okay, so basically, when I printed out the hand, I got 7 of clubs, king of spade, 6 of clubs, 4 of hearts, and 5 of spade. Is that fine? Okay, so if you do this again, obviously you'll get a different 5 card hand. You can see that. Is this fine? Is that okay?
Yes, Professor.
Okay, okay. Okay, so this random is actually very, very interesting and useful. Okay, so you can also draw random numbers from a triangular distribution. Okay, so let me talk about how the triangular distribution looks. So this is uniform distribution. I mean, we'll be again talking about a lot of it when I'll be just going over probabilities. But just to give you some idea about the functionalities of the random library, I'm just doing it. Okay, so triangular distribution is basically a distribution with a continuous it's a continuous random variable. Okay, so it's a continuous distribution, and it looks like this. Okay, so okay, so basically, for a triangular distribution, you have to provide what is the lowest value in the range of this random variable, what is the highest value in the range of this random variable, and what is the mode of it. So the mode is the one where the frequency is the highest. Okay, it's that value, for which the frequency is the highest. Okay, so if this is A, this is B. Okay, so A is, let's say, the low, this is high. Okay, this is low, this is high. Okay, and let's say M is the mode. Okay, in that case, the triangular distribution will look like this. Okay, so the density is going to be like increasing till you reach M, and then it's just going to start falling. Is that clear? Okay, so if you supply these 3 numbers, this is how the density function will look. Obviously, this height of the density will be chosen in such a way that the integral of of uh, of the density is actually 1. Okay, because if you integrate the density function over the range, you should get 1. Okay, so this area should be 1 basically. Okay, is that fine? Okay, so, have you all understood what is a triangular distribution? Okay, so now let's generate random numbers from this triangular distribution, and let's look at its histogram plot. Okay, let's see how is that going to look. Okay. So I'm going to use random.triangular. Okay, let's say low is 0, high is 1. Okay, and the mode is 0.9. Okay, is that fine? Okay, and let's generate one number from it for the time being. Oh, I haven't printed out. Okay, so let's just print out x. Okay, so this is we have generated one number from it. Okay, but let's look at the histogram plot. If we generate, let's say, a sample of size 100,000, or 1 lakh, how is the uh, basically frequency is going to look, and how is the histogram plot going to look. Okay, so let's do that. Okay, so again, n is 10 to the power 5. Okay, and this time I'm just going to create a list. Okay, and I'm just going to for underscore in range n. Okay, x dot append. Okay, this, and then just plt dot hist x. Okay, and then plt dot show, and let's see. Okay, not bad, right? Okay, this also looks pretty much triangular, right? Yes.
Yes, Professor.
Okay, and it's kind of because the mode was kind of around zero point 0.9, that's why you're getting something like this. Okay, I mean, there is a way to actually make smaller bins. Okay, so you can actually check out the documentation for hist. Let me again go back to Piazza. Okay. I mean, I'm doing this just because you have to keep checking the documentation. Whenever you need any function, you don't have to memorize anything. Okay, I mean, just check the documentation, and you'll get it. Okay, uh, so so you see that there's something called bins. You can actually supply how many bins you want. That's just going to do that for you. Okay, so let's just try that. Okay, bins equal to, let's say I want uh, 40 bins. Okay, let's just check. Okay, can you see that? Okay, with 40 bins, this is how it's going to look. You can even do 400 bins if you wish. Okay, and that's just going to be like kind of smooth looking, uh, basically like this. Okay, it's just begin to look more and more like triangular. If you pick 4,000 of them, I think that's too many. Okay. Okay, this is how it's going to look. Okay, I mean, of course, it has to be relative to the sample size. I mean, if you're going to make it too fine, then obviously you'll see a lot of ups and downs, because like these are too small, relative to the number of bins. Okay, so yeah, I guess 500 is just fine. Okay, is this fine? Can you see the triangle? Okay, so if I change the, again, this is because of law of large numbers, because you picked a large sample. The kind of sample that you have drawn, it is a representative sample of the population, so it has a similar kind of structure as the population, and that is why you can trust the large sample, to, I mean, provided it's drawn randomly. Okay, to okay, so if you just change the mode from zero point 0.9 to zero point 0.4, you can see that it will shift here. The top, of the triangle will shift to this point. So let's check this. Okay, and as expected, I mean, it's just the top of the hill is at point 4. Is this clear to everyone? Is that fine? Are you all here? Can you hear me?
It's clear, Professor. It's clear.
It's clear. Okay. Okay. Yeah. Okay. So let's continue. You can also draw random numbers from like normal distribution. Normal distribution, as you know, is actually one of the most important distributions in statistics. So let's do that as well, and then we'll move on to NumPy. Okay. Okay. So again, let's check the documentation. Okay, so this is for normal. Okay, so if you want to generate random numbers from normal distribution, you can use random.gauss. Okay, so and you just have to supply the mean and the standard deviation. Okay, that's all that you have to supply, because that's the parameter, right? I mean, these are the parameters of the normal distribution. So you just have to supply these two values, and it will generate a random number from this distribution. Okay, so let's just try to do that. Okay. Okay, let's first generate one value. Okay, let's say mu is 0. So standard normal. Let's pick standard normal. Okay, so mu is 0, sigma is 1. Okay, and let's print out the x. Okay, you can see that it's minus 0.469. That's basically, so if you keep running this again and again, it'll keep generating different values. Okay, from the same distribution. So let's see how the histogram will look. So all of you are aware of what is the shape of normal density function. What is the shape of normal density function?
Yes, Professor.
You are aware, right? Okay, so you've done statistics for economics. So let me just anyway show you. So it's going to look like this. We'll also do that in Python. We'll see how to plot the density function in Python, but let me just show you anyways. Uh, so this is how it will look. Okay, it will be symmetric around 0. Okay, and it will be like kind of a bell-shaped curve. Okay, and the peak will be at 0. Okay, so 0 is the mode. Okay, of the normal stand normal density function. Okay, and roughly around 68% of the values will lie between -1 and 1. So basically, probability with which a stand normal random variable takes value between -1 and 1 is close to 68%, and between -2 and 2 is close to 95%, and between -3 and 3 is going to be close to uh, you know uh, 99.7%. So let me just write that rule. Okay, 68%, 95%, 99.7% rule. Okay, so what I'm going to do is I'll generate some random values from this distribution, and plot a histogram, and just see if it has a similar shape as this density function. Okay, so let's check that. Again, I'll do the same thing. So n is 10 to the power, let's say 5, so 100,000. Okay, and again I'll create empty list. Okay, and then for underscore in range n, I'll just append, okay, x dot append, uh, well, just a random value that I've chosen from the normal density, okay, and then just use plt dot hist, okay, x, and let's say Benz is again, just 400, okay, and use plt dot show, okay. Okay, so let's run this. Okay, and as expected, I mean, this is precisely what we were, expecting, right? I mean, this is the the shape, is very much like, the population from which they are being drawn. So large samples are actually representative samples of the population, and this is because of law of large numbers. Okay, we'll see that in detail later on, but uh, this is a very very interesting result, and this is, um, and let's also do this. Let's check this. We know that this is true about standard normal, right? 68%, 95%, 99.7%. So what that means is the probability that a standard normal random variable takes value between -1 and 1 is 68%. Okay, and between -2 and 2 is 95%, and so on and so forth. So what we can do is this: we can actually figure out, you know what percentage of these x values are uh, between -1 and 1. Okay, okay. So how do you think you're going to do this? Okay, so again, you can actually generate a list, which will contain, which will contain value 1, if xi is between -1 and 1, and 0 otherwise. Okay, so you can do something like this. Okay, so let me just tell you how you can do it. I mean, of course, using NumPy it will be faster, but let's first do it this way, and then we can just see how we can just do this in one step in NumPy. I mean, this is also going to motivate, why we can actually use these libraries for doing operations in a faster way. Okay, so y equals, so again you generate an empty list, y, okay, and for I in range n, okay, because n is the length of x, right? I mean, so what you can do is you can just pick out the ith element of x, okay, and check if it is between -1 and 1 or not. If it is between -1 and 1, yi will take value 1. Otherwise, yi will take value 0. Okay. So this is how you can write it. If xi is less than or equal to 1, and xi is greater than or equal to -1, okay, then yi will be 1, else yi will be 0. Okay, so basically, by doing this, I have created this vector of ones and zeros, where whenever, the the ith position x, is between -1 and 1, the ith position y will be 1 and 0 otherwise. Now all that you have to do is just have to figure out kind of the proportion of ones that are there in this y. Okay, so that's very easy. You can actually use the sum of y, which will give you the total number of ones in y. Okay, and you just divide it by n, because that's the length of y. Okay, that's going to give you the proportion of uh, ones in y's. Okay, and then if you just print this out, that's going to give you the proportion of values in x that lies between -1 and 1. Okay, and it should be close to 0.68. That's because of, again, as I've told you, law of large numbers. But let's just check. Okay, so I guess there is some error. Sorry about that. Okay, so I haven't created a vector of, it was empty list, so I have to use append. Okay, yi, not yi. Okay, that's the reason. Now it should work. Okay, okay, not bad, right? Close to 68%. Is that okay?
Professor.
Okay, good. Okay, so now let me introduce NumPy. Okay, so again, instead of using NumPy everywhere, I'm just abbreviated it. So I'll be, using NP instead of NumPy, and then whatever method I want to use from NumPy, I just put NP dot whatever method, and uh, that's going to be enough. Okay, fine. Otherwise, you have to use NumPy dot everywhere. Okay, so that's basically the use of it. Okay. Okay, so again, let's check the documentation. Okay. So this is numerical Python. Okay. So we have already got it installed, so that's not a problem. Okay. Okay. So this is np.arrange. So it's basically an array. Okay. You know, so you can just put a list inside np.array function. Okay, and that's just going to convert it into a NumPy array. Okay, so basically the data type, like for example, you had list there. In this case, you'll be actually working with arrays. So you can call them arrays. Okay, so this is basically again, an array. Okay, this is also an array. Okay, but it's kind of a matrix. That you are creating by doing some operation like this. Okay. Okay, so let's maybe actually try some of these functions. Uh, you know, thing. Okay, let's start. Okay. Okay, so let's first take a list. Maybe 0, 1, 2, 3. Okay, and then just create an array. Okay, np dot array x, and let's print it. Okay, so even though it is printed like this, but it's an array. So if you want, you can check its type. Okay, type A. For type, if you type for figure out the type of x, that's a list. If you figure out the type for a, that is an array. Is that fine? Okay. So, what can we do with this, that we cannot do with the list? I mean, there's a lot, that you can actually do with this, that, is not easy to do with the, I mean, of course, you can also do a lot of things with the list as well, but this has added functionalities. Okay. Like, for example, if you just look at this X, and I do something like this, X greater than 1. Okay, and I'll ask you, okay, what is the result? Print X greater than 1. Okay, now X is 0, 1, 2, 3. So if you do something like this, there is an error, right? I mean, it's a list, you cannot compare it with an integer. It's an error. Okay, but if you do something like this with A, print A greater than 1. Okay, then what will happen is that it will create another array, which is basically going to just compare 1 with 0 first. So is 0 greater than 1? No, false. Okay, is 1 greater than 1? No, false. Okay, is 2 greater than 1? True. Okay, is 3 greater than 1? True. So it's just, I mean, so basically, you can actually do a lot of things with this, because otherwise, if you had to create this false, false, true, true, you have to write a loop, to actually accomplish that, but here you don't need to write a loop. Okay, I mean, you can just simply do A greater than 1. It will automatically create an array that you are interested in, so you can actually avoid a lot of loops, with arrays. Okay, and of course there are more functions, I mean, you can actually deal with the matrices, do matrix multiplication. I mean, there lot of stuff. We'll see that. Okay. So let's actually do this problem again. I mean, with the array. Okay. So we already have created this X, right? I mean, random.gauss. We already have created this X. Okay. So let me just do this again because I've overwritten it. You know. Okay, so it's close to 68% as we have seen over here. So what I can do is I can just remove this X. Okay, and this is basically the X that I'm going to use now. This is the sample that I've generated from sample of size 100,000 that I've generated from standard normal. Okay, and what I'm going to do is this, I'll just convert it into an array. Okay, and what I'm going to do is this, that I'll just, because if you see over here, I'll be comparing whether X is between -1 and 1, like something like that, right? So I can do something like this over here. I mean, uh, I can figure out, X is less than or equal to 1. Okay. Okay, so what I can do is this, I can just simply use np.sum. Okay, subtract from it. So again, sum is an inbuilt function in NumPy library. Okay, so you can actually x less than -1. Okay, so this is going to give me actually, like the number of x's which are between -1 and 1. Okay, the reason is because when you put x less than or equal to 1, so it is going to generate a list of trues and false. And the way Python recognizes true is, so Python recognizes true as 1 and false as 0. So if you put x less than or equal to 1, it's just going to take all the entries which are less than or equal to 1 and will create a new array with trues, with trues in the places where x is less than or equal to 1 and false elsewhere. Okay, so if you do np dot sum x less than or equal to 1, it will give me the sum of basically it will give me the total number of entries in x which are less than or equal to 1. And if you subtract that from total number of entries which are less than -1, you'll get the total number of entries between 1 and -1. Do you agree? Do you agree?
Yes, Professor.
Okay, so you can actually just do this and then divide it by n, and you should get the same thing. Okay, let's run this. Oh, I have to also print it out. Okay, so print this. Okay. Oh, should be A. Okay, sorry about that. As you can see, this is not going to work with a list, but it will work with an array. I have converted X into array by using A, but I haven't changed A over here. That's why I got this error. Because this is not supported for the list. Okay, but it is supported for arrays, so this should work. Okay, as you can see, we got the same result. Is this fine?
Professor.
Okay, okay. Okay, so let's explore more. So let's. Okay, so if you want to figure out what kind of data is stored in an array, you can actually use the inbuilt function d dot type. Okay, that's just going to give you what kind of data is stored in an array. Okay, so a dot d type. Okay, okay, a dot d type. If you just print that out, I think you should get a float. Okay, sorry about that. Oh, sorry. Yeah, you don't have to actually put these brackets. Okay. Yeah. So it's float. Okay. Is that fine? So the data that is contained in A is float. Okay. Now if I just consider B np dot array. Okay, and put 0, 1, 2. Okay. Now if you put B dot D type, print B dot D type. Okay, it should give you int, because it contains integers. Okay, okay. So is that fine? Okay, okay. So we can also check the shape, of an array. So let me define another array, which is np dot array. Okay. Let's make a list of lists. Okay, 0, 1, 2, 3, 4, 5. Okay, so first let me show you how it's going to look. Print a. So this is actually like a matrix. Okay, so it's actually 3 by 2. Okay, 3 rows, 2 columns. Okay, so if you want to check what is the data type, obviously you should get an int. If you want to check what is the shape, you can use a dot shape. Okay, and you'll get the shape. Okay, it's 3 by 2. Is that fine?
That's fine, Professor.
Okay, so you can actually do a lot of other things also. You can actually create a matrix of zeros. You can create a matrix of ones. by supplying the input, which is the shape. Okay, so let's do that. Okay, so a equals np dot ones. Okay, let's create a matrix of ones. Okay, so all that you do is just supply the shape. So you know let me just try this. If it doesn't work, then so let's say I want to create a matrix of ones with two rows and three columns. Okay, let me print a. Okay, so I think it takes a list as input. Okay, so let's just see. Yeah, this is fine now. Okay, so it takes actually a list as input, not a pair of numbers. Okay, so you have to supply a list where the first element of the list is 2, the second element of the list is 3. So that means first element is the number of rows and the second is the number of columns. So you can see that it created this uh, matrix of ones. Okay, so if you want to create matrix of zeros, you can do the same thing. you know np dot zeros. Let's run this. Okay, and that's what we got. Okay, so actually there are lots and lots of them. Okay, if you want to figure out the mean, okay, of the entries in a, so let me take this one. Okay, let's figure out the mean. Okay, so again, this is kind of quick. All that you do is just np dot mean a. Okay, so let me print a as well as print the mean of a. Okay, you can see this is a, and this is the mean of entries in a. Okay, uh, so you can also check. This is fine. Okay. Is that fine? Is that okay?
Yes, Professor.
Okay. You can also actually stack. So let me just show you. So suppose you have one array, you have another array, and you want to stack them to form a matrix. You can also do that. Okay, so let's just try that. Okay, a is np dot array, okay, and let's say it is 1 comma 2 comma 3, and b is also np dot array. Okay, and let's say it is 4 comma 5 comma 6. Okay, and then just do v stack. Okay, so c is np dot v stack. Okay, so it's like a vertical stack. Okay, let's provide the two arrays that I want to stack vertically. Okay, let's run this. Okay, I think. Okay, so again, it takes one argument. Okay, so I guess we have to use print out C. Okay, okay, and you can see that you can just create these vectors separately also, and then do a vertical stack like this. Okay, you can also do horizontal stack. H stack is the function that will work for that. Okay, so is this clear? And you can also figure out the shape. So this shape is very important. The reason is because when you do the matrix multiplication, I mean, it's always a good idea to check the shape. The reason is because you can only multiply the two matrices if so suppose A is a matrix, you want to post multiply A with B. So AB is what you want to find. Then the number of columns in A should be equal to the number of rows in B. So if you are basically trying to do some matrix multiplication, it is always a good idea to check the shape of the matrix. and then do the matrix multiplication. Okay, is that fine? Okay, let's talk about some more functions that you can actually use from NumPy. It's actually, like there's so many. I mean, it's just it has a huge list of functions. Okay, I mean, this is just like not even 1%. Okay, so np dot, you can actually create arrays like this. Np dot arrange. Okay, so np dot arrange is something which will like in which you just need to supply what is the lower limit, what is the highest limit, and what is the step size. So let's say you want to take a step size of 0.1. Okay, and if you want to print x, you'll get something like this. Okay, so you start with 1, and then the last value here is 29.9. Now you can see how easily you are able to do it. Otherwise earlier, you were actually writing some modification, some step size, then some loop to append the list, by epsilon. So here you can actually do it in one step. Okay, I mean uh, that's really beneficial. Okay, you can also do something like this. You can so here we are given the step size, which is zero point 0.1. But let's say, if you are given the lower limit and the upper limit, and you are given that, okay, you want a list of 500 numbers, between 1 and 30. Okay, then obviously you are not given the step size here. So one way is to actually compute the step size and then do it. Then another way is there is a direct function. You can actually use linspace. Okay, np dot linspace, and that will do the job for you. Okay, np dot linspace 1 to 30. Now let's say you want 100 of them. Okay, and then let's print y. Okay, and let's see. Okay, so this is what you'll get. So you basically take this entire interval from 1 to 30 and divide it into basically 100 equally spaced intervals, and then just pick their upper limit and lower limit, whatever, uh, and just form this vector. Okay, is that clear? Form this array. Okay, is that fine?
Makes sense, Professor.
Okay, now another very useful thing is you can actually if you want to, let's say, square array, then you don't have to write a loop. You can just directly put x star star 2. It will just square the entire array. Let's plot the graph of y equal to x squared. I mean, just to see how fast we can do it if we just use array. Otherwise we have to like write a loop to actually create a list of x's and y's and then plot it. But we can actually use array to do this faster. Okay, so let's say I want to plot a graph of y equal to x squared, where x takes value between -3 and 3. Okay, so what I can do is I can just use np dot arrange. Okay, -3 to 3. Okay, and let's say 0.01. Okay, so that's my step size. Okay, and y is what? X star star 2. That's it. Okay, and plt dot plot x comma y. Okay, and plt dot show. Okay, and then just run this. Okay, okay, and you can see this is a graph of y equal to x squared. Okay, so it's so much faster, than working with the lists. Is that fine?
Yes, Professor.
Okay. So you can also write, kind of a more efficient code to solve the utility maximization problem. I have actually posted it over here also. You can go over it. Okay, here I've used NumPy. Okay. Okay. So basically, if you just see this utility maximization problem, this is what you are interested in solving. So you have to solve this particular problem for these prices and income, and you have to sketch the demand curve. Okay. Of course, this is if you want to look at the theoretical solution, you can actually click on this. Okay, and you'll get the theoretical solution to this problem. Okay, so this is the theoretical solution to this problem. You can plug in the values in this particular function and check if the numerical values that you obtained from Python are kind of same or not. Okay, okay so this is how we can actually write the approximate demand function using NumPy. Okay, so I've just changed the function like name, underscore NP. So, this is actually quite quick. I mean, what you can do is you can just use np.arrange, because you'll be actually checking from 0 to m by px, all the values. So you can actually, create this array from 0 to m by px with epsilon step size. Okay, and then just create a y vector corresponding basically y array by figuring out what is m minus pxx upon py, and this np dot arc max is going to give you the position of the entry where this utility is actually maximum. Okay, so once you can access the position where the utility is maximum, then you can actually figure out what is x star y star, I mean, and that's it. It's just a small code, right? That can actually accomplish what we were earlier trying to accomplish using a loop. Here there is no need for a loop. Okay, and then you can just run this and plot the demand curve for x. Okay, this is the code which I've already shared with you. You can try that out. Okay, here I've solved this particular problem. Okay, 2 root x plus y. Okay. Is that fine?
Yes, Professor. Yes.
Yes,
Okay.
Professor.
Okay. So there are actually a lot of questions that I've posted over here. You can actually try them. Okay. Uh, so you can, if you want to see the theoretical solution, you can click on this link. Okay. This is another interesting Gini coefficient and Lorentz curve. If you are aware of it, it's fine. If not, then you can leave it, no problem. Okay, and this is Newton-Raphson method. Okay, for finding demand supply equilibrium. You can go over the code. You can just revise your Newton-Raphson method from the um, from Math for Econ, yeah, from Sid Sater and Heyman book. Okay, so and then you can just go over it and figure out how it is done. Okay, so you can actually click on it and you'll get to see the code. Okay, okay, so this is the problem. Okay, and uh, this is the implementation. Okay.